A tunnel boring machine, also known as a TBM machine, is a machine used to excavate tunnels with a circular cross-section through a variety of soil and rock strata. This is because tunneling with TBMs is much more efficient and results in shortened completion times. Drilling and blasting, however, remains the preferred method when working through heavily fractured and sheared rock layers. The first successful rectangular tunneling shield was developed by Mark Isambard Brunel and patented by him and Lord Cochrane in January 1818. Mark Brunel and his son Isambard Kingdom Brunel used it to excavate the Thames Tunnel beginning in 1825. James Henry Greathead was the first to ever build a patented cylindrical tunneling shield. Modern TBMs typically consist of the rotating cutting wheel, called a cutter head, followed by a main bearing, a thrust system and trailing support mechanisms. The type of machine used depends on the particular geology of the project, the amount of groundwater present and other factors. The largest diameter TBM, at 15.43 meters, was built by Herenknecht AG for a recent project in Shanghai, China. The machine was built to bore through soft ground including sand and clay. The largest diameter hard rock TBM, at 14.4 meters, was manufactured by the Robbins Company for Canada's Niagara Tunnel project. The machine is currently boring a hydroelectric tunnel beneath Niagara Falls. The machine has been named Big Beck in reference to the Sir Adam Beck hydroelectric dams to which it is tunneling to provide an additional hydroelectric tunnel. TBM typically consists of one or two shields and trailing support mechanisms. At the front end of the shield is a rotating cutting wheel. Behind the cutting wheel is a chamber. The chamber may be under pressure if open to the external pressure. Behind the chamber there is a set of hydraulic jacks supported by the finished part of the tunnel which push the TBM forward. The rear section of the TBM is braced against the tunnel walls and used to push the TBM head forward. At maximum extension, the TBM head is then braced against the tunnel walls and the TBM rear is dragged forward. Behind the shield, inside the finished part of the tunnel, several support mechanisms which are part of the TBM are located: soil or rock removal, slurry pipelines if applicable, control rooms, and rails for transport of the precast segments. The cutting wheel will typically rotate at 1 to 10 revolutions per minute, cutting the rock face into chips or excavating soil, usually called muck by tunnellers. Depending on the type of TBM, the muck will fall onto a conveyor belt system or into skips and be carried out of the tunnel, or be mixed with slurry and pumped back to the tunnel entrance. Depending on rock strata and tunnel requirements, the tunnel may be cased, lined, or left unlined. This may be done by bringing in precast concrete sections that are jacked into place as the TBM moves forward, by assembling concrete forms, or in some hard rock strata, leaving the tunnel unlined and relying on the surrounding rock to handle and distribute the load. While the use of a TBM relieves the need for large numbers of workers at increased pressure, if the pressure at the tunnel face is greater than behind the chamber, a caisson system is sometimes formed at the cutting head. This allows workers to go to the front of the TBM for inspection, maintenance and repair if this needs to be done. Under pressure, the workers need to be medically cleared for work under pressure like divers underwater and to be trained in the operation of the locks. Double-shielded TBMs are normally used in unstable rock strata, or where a high rate of advancement is required. Single-shielded TBMs, which are less expensive, are more suitable to hard rock strata. Urban tunneling has the special challenge of requiring that the ground surface be undisturbed. This means that ground subsidence must be avoided. This is discussed in much greater detail in section 6. The normal method of doing this is to maintain the soil pressures during and after the tunnel construction. There is some difficulty in doing this, particularly in varied rock strata. There are now several manufacturers of tunneling machines in Europe, North America and Asia, and they continue to develop new and improved machines.
Within the last few years, developments in mechanical tunneling have proceeded rapidly because of the increasing global demands for cities, federal states and nations which concern the extension of transport routes. The special requirement for the construction of the Nafsut Tunnel, northeast of Kermanshah in Iran, have led to a so-called double-shield TBM with a diameter of 6.73 meters. The TBM will drive an approximately 25.7 kilometer long freshwater irrigation tunnel to allow the cultivation of further agricultural surfaces. The following computer animation illustrates the functional principle of a double-shield TBM. Tunneling is carried out via a shield, which operates as advancing protection unit to secure the tunnel wall prior to tunnel lining. In the rear of the tunnel boring machine, in the tail skin, reinforced concrete elements called segments are installed. they provide the final one-layer tunnel lining, which secures the surrounding tunnel wall and protects the inside of the TBM and the staff working in that area. The overall system of the double shield TBM, deployed in Dasht-e-Zahab, has a diameter of 6.73 meters and measures 185 meters in length. The double shield TBM owes its name to its special design. A telescopic front shield is mounted on the front area of the TBM. The TBM area behind the shield is not moved during tunneling. The reaction forces which occur during tunneling, such as torque and longitudinal forces, are transmitted to the tunnel wall by extended gripper shoes, which are located in the intermediate section of the tunnel boring machine. The separated force distribution design allows installation of segments during tunneling, in contrast to common tunneling methods. After completion of one thrust cycle, the gripper shoes are retracted and the rear shield is pushed forward against the front shield. The displacement phase only lasts a few minutes. After that, the next tunneling cycle can start. Continuous advance, which means that the boring process can be carried out parallel to segment installation, guarantees high performance rates. The TBM can only drive in continuous mode in undisturbed geological formations, since the gripper shoes use the tunnel wall as support. The telescopic front shield can, therefore, only be extended in stable rock formations. Once the double shield enters fault zones, the telescopic front shield is retracted. Now the entire tunnel boring machine only advances with the help of the auxiliary thrust cylinders, which are pushed against the tunnel lining. This type of advance is described as a non-continuous advance, since an advance with the auxiliary thrust cylinders is only possible after completion of one segment ring, similar to a conventional shield. In fractured rock formations, this operating mode provides optimum safety. The operating mode allows adapting the machine to geological conditions and to achieve optimum performance rates in varying conditions. The sophisticated double shield technology of continuous advance requires additional detailed solutions with regard to design and mechanics. The cutter head is driven by circumferentially arranged frequency-controlled electrical motors. Each individual motor gear is engaged in the toothed ring gear of the main bearing. The installed drive power is 2100 kilowatts. The transmission of the torsion torque generated by the tunneling operations and the required thrust forces between front and gripper shield is particularly important for double shield design. The main thrust cylinders generate the longitudinal thrust forces, which connect the steel structure of the front shield with the gripper shield. The torsional forces generated by the tunneling operations are distributed to the steel structure of the gripper shield through two torque reaction cylinders. The torque reaction cylinders compensate the relative motion between the front and gripper shield. The gripper shoes are floating relative to the machine body. Two heavy hydraulic cylinders mounted between both gripper shoes force the gripper shoes out of the rear shield against the tunnel wall. The thrust forces and torsional forces are transmitted in the contact zones between gripper shield and gripper shoes. This allows a friction-locked connection and guarantees the final deflection of the forces. The cutter head of the double shield TBM is equipped with special hard rock cutting tools. 42 steel cutter discs, 17 inches in diameter, which are installed and supported on the cutter head, roll on the tunnel face due to cutter head rotation. Each disc is pushed against the tunnel face with 27 tons, thus breaking off the rock. The excavated material, so-called chips, fall into the tunnel invert. The spoil is taken up through 6 muck openings with buckets and lifted towards the top due to rotation. From here, the excavated material slides across chutes into the rear of the cutter head center. There it is discharged onto the conveyor belt through the muck ring. The actual lining operations in the excavated tunnel are carried out behind the shield. A complete segment ring consists of 4 reinforced concrete elements, called segments. The segments are turned by 90 degrees on the segment feeder and driven to the erector. The erector is controlled from a portable control panel with direct operator oversight. The segments are lifted from the segment feeder by means of a mechanical pickup plate. The auxiliary thrust cylinders are retracted prior to the installation of the next segment to allow a segment positioning in the next space. The next invert segment is installed and braced against the entire TBM system due to the immediate thrust of the auxiliary cylinders. After the installation of the invert segment and the top segment, the other segments are installed, displaced by half a segment width. The segment edges provide a self-centering installation, precise to the millimeter. Now ring build is completed, and the tunnel is growing ring after ring. HeronConnect, the technological leader in mechanical tunneling, has the know-how and experience to carry out any tunneling project. The company from Germany's southwest is the only provider worldwide that offers and markets the whole range of mechanical tunnel boring machines ranging between 100 millimeters and more than 15 meters in diameter. Contributing to HeronConnect's success, more than 25 years of experience and a worldwide service network make HeronConnect a competent partner.